Okay, I'm here to show you guys a brief video on the osmosis problems that are on page 120 and 121, and then also the osmosis in red blood cells on page 123 questions. So I'm showing you how to work those. Okay, so we're going to start off by showing a beaker. And in this beaker, we will put down the middle a semi-permeable membrane. And you all should know that a semi-permeable membrane means that this membrane allows certain molecules to pass and others not to, sort of like that dialysis tubing that you saw in the video. Along with these, we're going to assign a side A, side B, and we're going to give, so we're going to put a little thing on the side, which you can do very easily on your paper or wherever you want it to write it on your notes, and showing the concentrations involved in each of these. So we're going to put some solutions in here. One of them's, there's going to be two separate solutions, and we're going to see what kind of molecules pass to either side. Now, since our concentrations are usually reported in percentages, like 5% sodium chloride or 5% glucose, we're going to put something down here representing 100%. So on one side, let's pretend we have a solution that is 5% sodium chloride. Okay, so 5%. And on this side, we have a solution that's 3% sodium chloride. So the first thing you want to do is determine the concentration of the water, because we are given the concentration of the salt, 5 and 3. We need to determine the concentration of the water. So in this case, would be 95%, considering that if 5% is salt, then the remainder must be water. And on this side, 97%. The question might ask you, which way will the salt go? Since we have a higher concentration here and a lower here, we know that diffusion is when a substance moves from a higher concentration to a lower concentration. So in this case, the salt would go from A to B. That would be the salt, because we're going from 5 to 3. Eventually it would be 4 on this side and 4 on this side, and it would be in equilibrium, and we wouldn't have any net movement. As far as the water goes, we have 95% on this side and 97. So the water is greater here, so the water is going to move to the other side. So we would have water moving from B to A. So this would be from 97 to 96. And when it reached 95, that would give us an equilibrium when it reached 95 on both sides. That would be when the solution would be in equilibrium. So these kinds of problems aren't too hard. The only thing is that sometimes they they'll tell you in the question, they'll say, this semi-permeable membrane only allows water to pass, or allows only salt in water, or something different, where they give you specifics about that membrane. So because there are many different membranes in your body, different size pores in your membranes, they're going to allow some things to pass and others not to. So let's say I have a solution here, A and B, and I have something, I'm telling you that this only allows water to pass. And we have a 5% solution on this side of salt, and a 10% on this side. So we would still go through the steps of calculating the water concentration. On this side it would be 95, on this side it would be 90. Now I'm asking you, which way would the salt go? Would the salt go from B to A or A to B? Since this is a larger concentration, we would normally expect it to go that way, and we would say B to A. But we were told that this particular semi-permeable membrane doesn't allow anything to pass except for water. So salt would have to stay on this side. So we would still have salt. Salt would not move. But the water molecules would still be able to move. So we have 95 here and a 90 there. In this case, 95 is much bigger than 90, so the water would move in this direction. And it would continue to move until we reached 92.5 on both sides of it, so that the whole thing would be in equilibrium. But the salt concentration on side B would be higher than on side A. So the point of this one is to make sure that you read your directions. If it says only allows water to pass, then only allow water to pass. It doesn't matter how concentrated or dilute the solute is, you have to always focus on whatever is given to you. Okay, so now we're going to change this up a little bit. And those are how to work the problems on page 20 through 21, osmosis problems, where remember, you're always going to look at the water, because a lot of times they give you the concentration of the salt and then they just kind of slip, well, which way will the water go? And then you go, oh, that's easy. It's going to go, from here to here, because you forgot that they tell you about the salt, but they ask you about the water. So pay attention, do your calculations, and always know which way the water's moving. In this particular problems on page 123 that have to do with red blood cells, we're going to put a red blood cell in the center. And remember that their membrane that surrounds this red blood cell is a semi-permeable membrane. It allows some things in and keeps other things out. And it blocks other things. So here we'll set it up exactly the same way we set up the last one, because this would be like side A and side B. And we'll start off by putting 100% concentrations on both sides. Here, this one would be a red blood cell. And over here, we would have solution, because this is what our solution is. Okay, so I'm telling you that I'm putting this red blood cell in a 10% solution of sodium chloride. And the red blood cell is always going to be the same. It's going to be 0.9% sodium chloride. So when we do the math, we find out that this is 99.1% water. And this one is 90% water. 100 minus 10 is 90. So we know now that this water concentration is 90 and the salt concentration is 10. Here on the inside, the water concentration is 99.1 water and 0.9% salt, okay? So now I'm asking you, which way will the salt go? Will the salt go into the cell or out of the cell? Okay, let's assume that this membrane is permeable to salt, so we would say that here this salt concentration is much higher on the outside than in the inside, so the salt would go into the cell if it was permeable to salt, but we don't know if that for sure. But let's say now I'm asking you, which way will the water go? The water is 99.1 on the inside of the cell and 90 on the outside, so this is much bigger than 99.1 is much bigger than 90, so the water would leave the cell. And in this case, this is something we call hypertonic. And think of it, it causes the cells to crenate. That's a word that you need to know. It means shrivel up or lose all of its water content. So this would be called a hypertonic solution, where the salt concentration on the outside is much higher than the salt concentration inside the red blood cell. That's hypertonic. Okay, the next problem, we're going to use the same setup here. We don't even need to change the red blood cell, because that's not going to change. It's always going to be the same. Okay, so over here, we're going to change the solution in here. And this time we're going to add it to a 0.3% salt solution. So I would put 0.3. We'd calculate the water here would be 99.7. And then I would ask you, which way would the water go? Okay, so 99.7. In this case, we see that the water concentration is still 99.1. Here it's 99.7. So if I were to ask you which way will the water go, you would say that it would leave the solution and go into the cell. And just think of it like the cell being a balloon, because the plasma membrane is not that strong where it can withstand large amounts of pressure. So if I were to continually pump water into the cell, eventually this cell would burst, or what we call hemolyze. And in this situation, the solution is said to be hypotonic. It means it has a lower amount of salt content in it. So we call that hypotonic. And here the cells would do something else. They would not cremate, they would hemolyze, or hemolysis would occur. Hemo meaning blood, lysis means to dissolve or break down. So here the red blood cell would be broken down or dissolved, or I think of it as burst or exploded, but that would be a hypotonic solution. Okay, so that's the second condition, hypotonic. Now, there's one more, of course, isotonic. I'm just going to erase all this here and this stuff here. I don't need to do about the red blood cell because red blood cells don't change. I put my red blood cell back in here. I'm going to put it in a solution that is 0.9%, the same as this one. So my my water concentration would be 99.1. Here it's 99.1. So now I have something that is the same on the inside as it is in the outside, in 0.9. So I would have molecules entering the cell, but I would have just as many molecules of water exiting the cell. So this is when the cells are in equilibrium. This is exactly the kind of solution you want to take when you are in the hospital and you require to be hydrated. They hydrate you with something called isotonic water, or isotonic solution. And that is the same as, iso means the same, so it has the same tonicity as the red blood cell. So that is basically how you work these problems. So remember, always set it up with the beaker. If it's a red blood cell, just draw a little red blood cell in the center. If it's a semi-permeable membrane, then just draw a line. And then describe the two solutions on each side, do your math, and you should be able to tell quite easily which way the water will go. Okay, so I'm going to erase that, and I'm going to give you my little mnemonic that I use for remembering these things. Okay, so the first one we looked at was a hypertonic solution, and I always remember this by making my R a little bit bigger for hypertonic, and that would tell me, when I see that R, I know that that causes cells to turn into raisins. And so hypertonic causes cells to become raisins or shrivel or lose their water, or crenate is the word we're using. The second type of solution is a hypotonic solution, and that causes your cells to explode. So I always think the O as a bomb, causing the cells to explode or hemolyze. Hemolysis occurs. And then, of course, isotonic is just nothing happens because the cell is the same on the inside as it is on the outside, so nothing happens. This is the one you want to go with each time. When you go to the hospital, they're going to give you isotonic. If they tell you, oh, you can have hypertonic or hypotonic because we're plumb out of isotonic, which one would you prefer? Try to think about that. So the way that I remember it, and something a little bit easier than drawing it out like that, is just make this little box on your paper and put these two little greater than or less than signs. And in the center, you're going to put the salt concentration for a red blood cell. So it's 0.9. Now anything greater than that is going to cause the cell to shrivel up or crenate. Anything less than that, than 0.9, is going to cause the cell to explode. Okay, so you can, when you think of a raisin, you can draw it so you can visualize it. Okay, so that means if I give you a question and I tell you I'm dropping a red blood cell into a solution that is 10% salt, you'd say, okay, 10% is much bigger than that. This is going to cause the cell to crenate. And I know cells crenate when they're in a hypertonic solution. If I told you I'm going to drop a red blood cell into just plain old tap water where there was no salt, then you would say, okay, 0 salt is less than 0.9. So my cells are going to explode. And why would they explode? Because all the water is going to be pumped into the cell, and it's going to keep going in there because the salt concentration in the inside is greater, or the water concentration is less in the inside than on the outside. So water is going to move from an area of greater concentration, 100%, to an area of lesser concentration, 99.1. So this would definitely cause the cells to explode. So if you can remember those two, this little drawing here, then you can, anytime I throw out a problem, such as the problems on page 123, number 5, the top of 123, problem number 5, those can easily be answered just by looking at this, okay? So you can answer problems that are a lot easier. They'll be a lot easier for you to visualize and handle if you can remember this simple little drawings that I have here. And that's all I have for you today. I hope this helps. I will have a attendance question about this, so make sure that you watch it and answer your problems. There will be problems on the quiz and on the test on this type of tonicity, which is hypertonic, hypotonic, and isotonic. Thank you.